Hello Math HL students, this is Mr. Chun. This is the first video that I've done this year, so congratulations. We're going to be talking today about vectors, and in particular 3D vectors and the operations on vectors in space. Okay, so the sections that we're covering are 14G and 14H. You can follow along in your textbook as you watch this video. But 14G, we're going to talk about the 3D coordinate system, how to find the magnitude of a vector in 3D, and being able to find the vector in between 2 points. We're going to talk about vector equality, when are vectors equal, and 14H will cover the operations on 3D vectors. So let's start with the 2D coordinate system and then extend it into the 3D coordinate system. The 2D coordinate system we're all familiar with. It has an x-axis and a y-axis, and you've learned about this since grade 6, right? Well, the 3D coordinate system is very similar to the 2D coordinate system, except we have a third axis. Okay, so notice that the arrows, right, and this is the positive direction and that's the positive direction. So just like the 2D coordinate system, in the 3D system, our x is going to be this axis, our y is going to be this axis, and our z will be our third axis, and that points up out of my xy plane, right? Something to remember here is that the this is always 90 degrees, and this is always 90 degrees, and this is always 90 degrees. Okay, so the three axes are mutually perpendicular, and that just means they're always 90 degrees with each other. All right. The xy plane you can think of as the tabletop, and the z-axis is the axis that's pointing out of the page, or out of the tabletop. And this is what your book does as well. My line's not very straight here, but they like to use these dotted lines to indicate the negative direction. So you can go backwards away from your arrows. So just keep that in mind as you do this. All right, so that's really it. Let's do a couple examples on the next slide of how to plot points in the system. Okay, so plotting points on the 3D coordinate system looks like this. Here we have a point P, and its coordinates are some x, some y, and some z. Okay, we're going to assume just for this picture that x, y, and z are positive values. And you can see here that you're starting at the origin, and we're going in this direction first in the x direction, so we're going a positive x distance, then we go a positive y distance in the direction of the y-axis, and then we go up in the direction of the z-axis, z number of units to get to our point P. Okay, so always go in order, just like we do in on the 2D system. Just like we go, we always go x first and then up, right? We always kind of do that. So it's the same idea. We're just going one step further and going along the z-axis last. Okay. And if it's hard for you to visualize this, you can always draw a rectangular prism, which is kind of fun. Okay, so after you've drawn your point, you can kind of draw these rectangular prisms to kind of indicate, where that is spatially, to visualize it. Okay, so you can always, have fun drawing cubes. If you like drawing cubes, then this is a good thing for you to do. And any point P that's given as an ordered triple, we can change into the form of a position vector. And the position vector of a point P, it always goes from 0, right? And we saw this when we did our 2D vectors. So we always start from 0 to P. It'll be our x, y, z values. Remember, our tip minus our tail values, which is our origin, which is 0, 0, 0. So it just turns out to be OP is x I hat plus y j hat plus z k hat. Okay, and so you can remember that these are our unit vectors that go in a certain direction. The I hat vector always goes in our x positive, sorry, let me use a different color here, a positive x direction. Okay, so you can kind of think of this as my I hat. Let's use a different color here for j. J hat always goes in the positive direction along the y-axis. Okay. And oops. Okay, and the z-axis, or the k hat, always goes in the positive z direction, and we'll call that k hat. And these are unit vectors; they are all a distance of 1. Okay, so we're going x units in the I hat, x number of units in the I hat direction, plus y number of units in the j direction, and z number of units in the k direction. Okay? Alright, so let's try some examples here. Let's illustrate these points on an axis. Okay, so let's start with A. Okay, we're going to draw A. We're going 0, 0. Let's draw our axes here. We're going to go 0 in the x direction, so we're not going to move from our 0 in the x direction. We're going to go 2 units. Again, I'm just sketching here. We're going to go 2 units in the y direction, right? And then we're going to go 0 units up. So really, my point ends up being this point right there. Okay, and that will be my A 0, 2, 0. Okay. Let's try part B. And you can pause this video to test yourself anytime you want. Okay. Let me just erase this. Sorry, let me just be consistent here. For B, would go 3 in the x direction, right? 1, 2, 3. So we would go from here, in this direction. 0 units up in the 0 units in the y direction, right? This is my y value. So we would not go in this direction at all. And then we'd have to go up 2 units. So really we're going from here up 2 units, and that would be my final resting point for my point B. Okay, so that would be 3, 0, 2. Alright, and I guess I could use a different color there to indicate where that would be. Okay, alright, let's do the last one. C is going to go, now we're going to introduce negative numbers. So x, y, z. We're going to go back. We're going to go negative 1 in the x direction. So if that would be negative, if that's negative 1, we're going to go that way. That's negative 1. We're going to go 2 in the positive y direction. 1, 2. Okay, so then that's our second kind of resting point. And then we're going to go up 3 units, and this is where it gets kind of tricky because you have to be kind of good at drawing, I guess. 1, 2, and 3. I'm not very good at drawing here, but that would be an approximate, sketch of the point C. So you'd have C, negative 1, whoops, negative 1, 2, and 3. Okay, and if it's hard for you to see that, you can always draw. You can always kind of draw the rectangular prism to help you with that. Okay, so you just want to make sure that you're drawing straight lines parallel to your axes. Okay, and there you go. Now it's a little bit easier for you to see, and I'll go ahead and color that point in as well. Okay. Alright, the magnitude of a vector, we know from the review session that we did last class that in 2 dimensions the magnitude of a vector is found by using this formula. We're really just using Pythagoras' theorem. Okay, and the magnitude is always the length of the vector, right? So that distance is really the magnitude of my v vector. Okay, this would be kind of like my v1, this would be my v2 values, right? Well, in 3 dimensions it's exactly the same thing, except we're doing the Pythagorean theorem twice. Okay, if you look at this picture over here, we're going to go from the origin all the way to point P. Okay, so if I want to find this distance, I have to use Pythagoras' theorem with this height C and with this bottom leg, I guess, of the right triangle. To find this, I have to find the square root of a squared plus b squared, and so this squared plus that squared, and then you take the square root of that to get the magnitude. Okay, so that's how you'd end up with v1 squared plus v2 squared plus v3 squared, which is kind of nice. All you have to do is you take that third value and square it. Okay. Same thing with the vector between 2 points. In 2 dimensions, the position vector of B relative to A. Okay, so if we have 2 points, A and B, okay, we always take the position vector of B. So B comes first, the tip comes first, right? This is my tip, and then we subtract that vector, the tail vector. Tail vector from the tip vector. Okay, so OB minus OA is going to be the vector of B relative to A. So if I'm going from A to B, right? Same thing in 3 dimensions. Can you guess what it's going to look like? Yes, it's just going to have this extra little piece here. Okay, and there you go. AB, the vector AB is the OB vector minus OA, the OA vector. Okay, so very, very easy as long as you understand how to find the vector between 2 points in 2 dimensions. If you're having trouble with this, you might want to go back to the previous sections. I believe it's 14D. Okay, so let me just write that in here. This is section 14D if you're confused on this part right here. Okay, so if you need more practice, go back to this section. Okay, let's try an example. It says here P is a point and Q is also a point with these coordinates, right? So we have 2 points, and we're supposed to find, for the first part, we're supposed to find OP, the vector OP. Okay, so it's really the exact same thing that we did in the 2D system. We're going to look at the point P and take away the values of point O, which in this case is 0, 0, 0. So we really end up with -3 minus 0, 1 minus 0, 2 minus 0. We end up with this. Okay, so this is our OP vector. So anytime you're looking for the position vector, remember that this is the position vector of P from O. Then you can just really write the coordinates just in a vertical form. Okay, and then part B says, well, find now the vector PQ. Okay, so again we're going to do the same thing that we did in part A, except this time instead of O, we're going to be using P, and instead of P we're going to be using Q. So Really what we're going to be doing is we're going to be taking the coordinates of Q and subtracting from those coordinates the coordinates of P, and then rewriting it in this form. Okay, so your answer will end up looking like this. So we're going to be taking 1 minus -3, -1 minus 1, and 3 minus 2. Okay, and then you end up with this. So it's really just basic arithmetic. So you end up with 4, -2, and 1. And then now for part C, we're supposed to take the magnitude, okay? Don't confuse this with absolute value. This is when we're talking, when the inside here is a vector, we're going to say this means magnitude, okay? Magnitude. And so the magnitude of PQ is, remember from the formula, we said that it's just going to be kind of like the Pythagorean theorem, but because we have 3 values, we're going to be squaring each of those, adding them up, and then taking the square root of those. We end up with this. So take 4 squared plus -2 squared plus 1 squared, right? All of these. Take the square root of that, and that's how we find the magnitude. Okay? Let's talk about vector equality. How do we know that two vectors are equal? Again, it's going to be the same thing in 3D as it is in 2D. Two vectors are equal if they have the same magnitude and direction. Just a note here, if they have the same magnitude and direction, they're going to have the same components. Okay, so the x components, the y components, and the z components are all going to be equal. And remember that you can move vectors around. Okay, you can always move vectors anywhere in space, and they can still be equal. Okay, and if this little theorem here says if A and B don't coincide, then they're going to be opposite sides of a parallelogram. Right? They're always going to form a parallelogram, and they're always going to line the same plane. You can always create a plane using those two vectors. So let's try an example here. Okay, it says ABCD is a parallelogram, and we have these 3 points, and we're looking for the 4th point. We have A, B, and D, and we're looking for C. Okay, so let's think about how we're going to solve this problem. We're looking for the coordinates of C, and we have 3 other points. Now, remember that this forms a parallelogram, so we have to think back to vector equality here. We know that because it's a parallelogram, we can create some vectors, right? And all of these are going to lie in the same plane. So we don't really need to draw this to scale. We can actually just create, knowing that we have 2 vectors pointing in a certain direction, we can kind of reorient that plane so that we're looking down on it, and we end up with a parallelogram. Okay, so we're going to go in order. We're going to start with A, B, and then we're going to create C, and then go to D. Okay, so we're going to go A, B, something like this, and we're going to go in the order that it's been written in. Okay, and we'll create some variables for point C. So let's let C be the coordinates A, B, C, little a, little b, little c, and we can create this diagram here. Okay, because it's a parallelogram, we also know that these 2 vectors, okay, these 2 opposite sides of the parallelogram are going to be parallel, and they're going to be equal vectors, really. Okay, so we can state this. We can say segment AB is parallel to segment DC. This is the notation for a segment, which is slightly different from our American style notation, but this is perfectly acceptable. So AB is parallel to DC, and they have the same length. So the vector DC from D to C is going to be the same as the vector from A to B. So we can if we can find the coordinates of DC, or sorry, the vector that represents DC, then we can find we can equate that to the coordinates of the vector AB, right? And so we know AB is going to be what? AB is going to be the coordinates of B minus the coordinates of A, right? It's going to be 2 minus -1 for the x coordinate, 0 minus 2, and -2 minus 1. So we could write that on this side. For DC, we can, because we've defined these variables as the coordinates of point C, we can say these values minus these values. And that's what we get it here. Okay. You can see on this side we have 2 minus -1 is 3, 0 minus 2 is -2, and -1 minus 1 is -2. So now we have this system. We have the, well, yeah, it's not really a system yet, but we have these two equal vectors. And so by the vector equality rule that we looked at earlier, we can say that because these two are equal, their coordinates have to be equal, and so we end up with three nice equations that we can write out separately. Okay, so we end up writing them separately as a minus 3 is 3, b minus 1 is -2, and c minus 4 is -2, and we solve those to get the coordinates. So c then becomes 6, -1, and 2. Notice that the notation here, we've written it as an ordered triple. Okay, we haven't written it in vector form because it's not a vector. C is not a vector. C is a point with these coordinates. Okay, and just something else for you to think about to kind of verify your method. Okay, you could check your work by using the midpoints of the diagonals of a parallelogram. Right? Remember that a parallelogram's diagonals will bisect each other. So using a little bit of geometry, you're going to be able to remember that this segment and this segment will bisect each other, so they should have the same midpoint. Okay, so you could do a little bit of geometry there to test your calculations, and you can look in your book. It's in example 22 on page 407. Okay, and that shows you how to do this method as well. Okay, so 12H, section 12H is operations with vectors in space. So now we've talked about the 3D coordinate system and finding the vector between 2 points, how to set two vectors equal to each other, magnitude of a vector, that kind of thing. Well, now we're going to be talking about, let's do a little bit of algebra with vectors in space. Okay, and so the same rules are going to apply for 3D vectors as they do for 2D vectors. We're going to say if A is A1, A2, A3, and B is B1, B2, B3, then when we add these two vectors, we can simply add their coordinates, their unit vectors. We can add their unit vectors, which are A1 and B1, together to get the x value for our resultant vector. Same thing with subtraction. We can simply take the difference of those coordinates. Okay, and also for any vector, we can change its length by multiplying by a scalar value k, okay, where k is actually going to be a real number. Okay, and when you do that, you can simply multiply k to each component. All right. Here are some properties of vectors. There's a nice little investigation in your book on page 409 that you can try out on your own time, maybe just to get a little bit of a better sense of these properties. But in essence, they're really not any different from, or not all of them are. Most of these are not any different from regular algebra. Okay, so if I have a vector A plus a vector B, we can say that vector B plus vector A is going to be the same thing. So that's the commutative property. We have the associative property, which means we can regroup. Okay, for addition, we have the additive identity. If you add 0, the 0 vector, you're just going to have the same vector. The additive inverse. Okay, you can, if you subtract a vector from it. If you add a negative vector to itself, you're going to get 0, the 0 vector. Okay, so we all know this. This line here might be a little bit confusing, or something that you might need to think about a little bit more. The length of Ka, okay, we're going to use the same symbol in this book, but when it's around a scalar, when these marks are around a scalar, that means the absolute value or modulus. When it's around a vector, it means the magnitude or length of the vector. Okay, so notice this is a vector, this is a vector, so we talk about lengths or magnitudes. Here, this is a scalar, so we're not going to take the, we can't really do the magnitude of a scalar. So it's really just taking the absolute value of that K value. Okay, and then the distributive property works with vectors as well, assuming K is a scalar value. Okay, a note about vector algebra. If I have 2x equals a, okay, 2 times, notice that x and a are both vectors. If I have 2 times x is a, then x is half of a, okay? So and it's not a over 2, okay? This is something that you do normally in regular algebra, but in vector algebra, this does not really mean anything, okay? Because you can't have a vector divided by 2. We say half of, we have to talk about this as a K value, okay? Also, a note about vector notation. Some of the other students make this mistake a lot. But if I have a point, let's call it x, y, z, okay, and this is a point. The notation that we use for a point, I'm just going to call it, let's call it a, okay. If that's the point, okay, and this is very different from this, okay. So this is the vector, this over here is the vector notation, and you should always, to not get confused, you should always write that. And this is the point notation, okay? This represents a point, this represents a vector. So if I write it like this, recognize it's a vector. So on your test, please do not write this, or sorry, don't write this as a vector. Don't say this is a vector, okay? Because that's a point. All right. Okay, so let's try this problem. If A is equal to, if A is the vector with coordinates -1, 3, 2, find the magnitude of 2A. All right, so the first step, there's a couple ways to do this. We can, just by looking at this, we can figure out that we're going to have to double the magnitude, or sorry, double this vector, right? We're going to have to multiply this vector by 2 and then find the magnitude. Or you can use that rule that we had earlier that said the magnitude of Ka, where A is a vector, is the same as the absolute value of K. Remember, K is a scalar times the magnitude of A. Alright, so you could use this, or you can go ahead and find 2A first and then find the magnitude. Alright, this turns out to be a little bit easier because finding the magnitude with smaller numbers is easier. So, alright, so let's go with that. Let's go with this method. So we can take out the 2, and then we can find the magnitude of A, right? And then multiply that by 2. We end up with 214. Okay. All right. Okay, here's a harder problem. It says find the coordinates of C and D given that we have this line here and the points A, B, C, D are all on this line. Notice that A and B are next to each other. Then we have C and D, and we have 3 equal segments between these points. So let's think about this. How would we solve this problem? Can we see any relationships? Right? Can we see any relationships? Well, yes, we can. We can see that the points AB. Okay, so this length is the same as this length and the same as this length. So maybe if I can find the vector between A and B. I know how to find the vector between 2 points, right? Maybe if I can find that, then I can find use that vector to find the point C, and then use that vector to find the point D, right? So let's see how we can do this. We'll start by finding AB, the vector AB, and this we do by taking the coordinates of B and subtracting the coordinates of A, right? So we go -1, -2, -1, -2, and so on. Okay, and we end up with the vector going from A to B is 1, 3, and -1. So that's this vector right here, right? We're going from A to B. Okay, well, I know that this length is the same as this length, so really I could find the vector AC. Okay, the vector AC is really 2 times vector AB, isn't it? Right, because it's going in the same direction and it's twice the length of AB. So there's one relationship that I know. And if we think about this, now we have 2 points, right? We can find the vector between this. Or we know that let's say the origin's over here. Okay, if we have the origin over here, and I'm just drawing arbitrarily here, I can find vector. If we call that O, we can find OA, right? And we can also find OC, right? So OC turns out to be equal to OA plus AC, right? We see that relationship here. We're going this vector, right? We're going this vector plus this vector is equal to that vector. And we did that when we did geometric operations with vectors, and the same thing applies in 3D vectors. So once we have this relationship set up, and we know that AC is going to be 2 of AB, the vector AB, then we can simply do some adding of components to figure out OC, right? Okay, that's what we're going to do, and OC turns out to be OA plus AC. We can replace that here, and OA is simply these coordinates rearranged in vector form, or component form, and then 2 times AB, which is 1, 3, -1. And then we can add that, and now we have 0, 1, 1. This is, remember, this is like if O was over here, that's this vector, okay? That's this vector here, and that's the position vector of the point C. So we can say that C then is going to have the coordinates of 0, 1, and 1, right? So that's this part right here. We've done that part. Alright, the same rule applies. We can find, if we assume that O is somewhere over here, we can say, well, we want to find the coordinates of D, so I need to be able to find, if I can find the position vector from O to D, and I know OA is over here, and I know that this vector is AD, alright, then I can set up a relationship again. OD is equal to this vector plus this vector, the OA vector plus AD, right? Okay, so it's really the same problem as what's over here. Okay, it's the same problem, we're just doing it again, and this time AD, we know that AD is going to be what? It's going to be 3 times AB. Okay? And there you go. We have 3 times AB, so we'd have to multiply this vector by 3, and then add these 2 vectors, and we get 1, 4, 0, and therefore 1 has the coordinates of 1, 4, 0. Okay? Okay, last problem, number 12. In your textbook, it says if AB is this vector, okay, and we have AC as another vector, and we have BD as another vector, find the vector AD and find the vector CB, okay? So now we're given some vectors, we're looking for another vector, probably some kind of setup. We have to somehow set up AD is equal to something, right? That's what we're looking for. We're going to find AD is equal to what? Okay, so we're going to probably have to set up a relationship here just by looking at well, I mean, I could do this by graphing it, but it would just take a long time because I'd have to go through the coordinate system, drawing it and everything. So let's just look at these letters here, and we can figure it out, right? When we talk about vector addition, we can just look at the letters, and as long as we start with A and then end with D and add up all the vectors in between, all the stuff in between, we should be able to find an equivalent vector. Okay, so let's start with we know that AB, we have an AB and an AC, right? We have AB here, AC, and BD. Well, this one ends with D, so we're probably going to have BD. Okay, so we're probably going to add that to somewhere. And we have AB here, so that works out nicely. We have AB plus BD, okay? And remember that if we have B and B here, we can these will sort of cancel out to get AD, okay? So let's just go ahead and substitute that in. AB is -1, 3, 2, plus BD is 0, 0, 2, and -3. Sorry, my stylus is not very good. And then we just simply add the components up. So we end up with -1, right? These two, add those, add those, add those. So we have -1, 5, and -1. Okay, and that's my answer for AD. Okay. For part B, we're looking for CB. Now this time we have to start with C. Okay, so we have to start with a C somewhere. So we have to start with some vector that starts with C. We're going to add that to some vector that ends in B. Okay, so we have an AB over here, so we're probably going to have to add an AB. Alright, what letter can go in here? Well, we have an AC. Can I convert this into an CA? Yes, I can. I can just simply flip it, right? I can flip it, which means I'm going to change all my components to negative of what they were before. So let's write that in, CA. Okay, so we're going to write, well, that's the same as really negative AC, isn't it? Okay. So if we write negative AC here, we're going to have -1 times 2, -1, 4. And AB turns out to be -1, 3, 2. Okay, we simplify this. We multiply this through into each term, or each component. We end up with -2, 1, and -4. We're going to add that to 1, 3, and 2. And then we end up with -3, 4, and -2. Okay, so that's my CB vector. Alright, so those are my two answers right there. Okay. Alright. So that's it for this lesson. We've talked about the 3D coordinate system and how to do all the operations on a 3D vector. Okay. How to find the magnitude, find the vector between 2 points, and knowing when two vectors are equal. Alright. This is your assignment. Please go ahead and try those problems. If you have any problems with them or any issues, write down your questions, post them on Schoology, or bring them to class. Alright, thanks guys.